Welcome back. Today we're exploring the infrastructure needed to train large language models, the systems, hardware, and engineering that make it all possible.
Training frontier LLMs is one of the most complex engineering challenges in computing.
Let's start with the hardware. What do you actually use to train these massive models?
The workhorses are GPUs and TPUs, specialized processors designed for parallel computation.
GPUs or graphics processing units were originally made for rendering graphics but are perfect for the matrix operations in deep learning.
NVIDIA's data center GPUs, like the A100, H100, and upcoming B100, are the most common.
A single H100 GPU has 80 gigabytes of memory and can perform hundreds of teraflops of computation.
But one GPU isn't nearly enough for training large models. You need thousands.
A typical large scale training run might use 1000 to 10,000 GPUs running for weeks or months.
TPUs, or tensor processing units, are Google's custom chips designed specifically for machine learning.
TPUs are organized into pods, large scale clusters optimized for distributed training.
They offer high performance and tight integration with Google's training stack.
Other companies are developing custom AI chips, AWS Trainium, Microsoft's Maya, and various startups.
The goal is to optimize for the specific operations needed in LLM training.
Now let's talk about distributed training. Why is it necessary?
Models with billions of parameters and their optimizer states don't fit on a single GPU.
Even if they did, training would take impractically long.
Distributed training splits the work across many devices to both fit the model and speed up training.
There are several strategies for distributing training.
Data parallelism replicates the model on each device but gives them different batches of data.
Each device computes gradients on its batch, then gradients are averaged across devices.
This scales well as long as batch sizes can grow proportionally to the number of devices.
Tensor model parallelism splits individual layers across devices.
For example, you might split a large matrix multiplication across 8 GPUs.
Each GPU computes part of the operation, then they communicate to combine results.
This allows models larger than a single GPU's memory.
Pipeline parallelism splits the model vertically into stages.
Different layers run on different devices.
As one stage finishes processing a batch, it passes activations to the next stage.
This is like an assembly line. Different parts of the model process different mini batches simultaneously.
There's also sequence parallelism for very long sequences.
The sequence dimension is split across devices.
Most real systems combine these strategies, a hybrid approach.
You might use data parallelism across nodes, tensor parallelism within nodes, and pipeline parallelism for very large models.
Let's talk about optimizer state sharding.
Optimizers like AdamW store momentum and variance for each parameter.
This can triple the memory requirements compared to just storing parameters.
Zero, which stands for Zero Redundancy Optimizer, partitions optimizer states across devices.
Each device only stores optimizer states for a subset of parameters.
Zero has multiple stages, sharding optimizer states, then gradients, then parameters.
FSDP, fully sharded data parallelism, is similar and is widely used in PyTorch.
These techniques dramatically reduce memory per device, enabling larger models.
Now, communication is critical in distributed training.
Devices need to exchange gradients, activations, and other data constantly.
The communication bandwidth and latency matter tremendously.
High speed interconnects like NVIDIA NVLink within nodes and InfiniBand between nodes are essential.
These provide hundreds of gigabits per second of bandwidth.
Communication can become a bottleneck if not managed carefully.
Gradient accumulation helps compute gradients on multiple batches before communicating.
Overlapping communication with computation also helps hide latency.
Let's discuss fault tolerance.
When you're running thousands of GPUs for weeks, failures are inevitable.
A GPU might fail, a network link might drop, or software bugs might crash processes.
You need checkpointing, periodically saving model state so you can resume from failures.
Checkpoints include model parameters, optimizer states, and training progress.
They can be very large, tens or hundreds of gigabytes, so saving and loading them efficiently matters.
Some systems use asynchronous checkpointing to avoid stopping training.
There's also automatic recovery, detecting failures and restarting from the last checkpoint.
Let's talk about data pipelines.
You need to continuously feed training data to thousands of GPUs.
The data must be tokenized, batched, and distributed efficiently.
Data loading can become a bottleneck if not optimized.
Pre-processing, caching, and parallelizing data loading are all important.
Some systems stream data directly from distributed storage like S3 or GCS.
Others pre-process everything and store it in optimized formats.
Now, let's discuss monitoring and debugging.
When training at scale, you need extensive monitoring.
Track loss curves, learning rates, gradient norms, and throughput.
Watch for anomalies like loss spikes or gradient explosions.
Monitor hardware health, GPU utilization, temperature, memory usage.
Logging and visualization tools like TensorBoard, weights and biases, or MLflow are essential.
Debugging distributed training is notoriously difficult.
Errors might only appear at scale, not in small tests.
Reproducibility is challenging because different parallelization strategies can give slightly different results.
Let's talk about software frameworks.
PyTorch and JAX are the most common frameworks for LLM training.
PyTorch has extensive ecosystem support and is widely used in research and industry.
JAX is favored by some for its functional approach and XLA compilation.
There are also higher level libraries like Megatron LM from NVIDIA, DeepSpeed from Microsoft, and others.
These provide optimized implementations of distributed training strategies.
They handle the complexity of multidimensional parallelism, memory optimization, and communication.
What about containerization and orchestration?
Docker containers package the training environment for reproducibility.
Kubernetes orchestrates containers across clusters.
Some organizations build custom orchestration for training jobs.
Job scheduling, resource allocation, and priority management become important at scale.
Let's discuss costs.
Training a frontier model can cost tens of millions of dollars in compute alone.
If you're renting cloud GPUs at 2 to 4 per hour each and you use 10,000 GPUs for a month, that's tens of millions.
Some companies own their own hardware to reduce long term costs.
But that requires huge capital investment, data centers, cooling, power, networking.
Power consumption is massive. Training runs can use megawatts of power.
This has both cost and environmental implications.
Efficiency improvements, better algorithms, hardware, or parallelization directly reduce these costs.
What about cloud versus on premise infrastructure?
Cloud offers flexibility. You can scale up for a training run and scale down after.
On premise gives more control and can be cheaper long term for sustained use.
Many organizations use hybrid approaches.
They might do development and smaller experiments in the cloud, but run major training on owned hardware.
Let's talk about inference infrastructure, which is different from training.
Inference needs to be low latency and cost effective for serving many users.
Systems like VLLM, TGI, or RayServe optimize for inference throughput.
They use techniques like continuous batching, where you batch requests dynamically.
KV cache management, quantization, and parallelization strategies differ from training.
Inference might use fewer but more cost effective GPUs or even CPUs for smaller models.
Autoscaling handles variable load, scale up during high traffic, down during low.
So, to recap, LLM training requires specialized hardware like GPUs and TPUs, distributed training strategies, split models, and data across thousands of devices. Communication, fault tolerance, and data pipelines are critical infrastructure components. Software frameworks and libraries handle the complexity. Costs are enormous in compute, power, and engineering effort, and inference infrastructure has different requirements from training.
Next episode, we're exploring data curation and cleaning at scale, how to build high quality training datasets.
Thanks for listening.
Until next time, keep learning and stay curious about AI.